Hello, everybody. It's me again, Michael Leclerc. Going to be talking to you this week in week 11 of environmental concerns about climate change versus global warming. So we got this cute little comic here, and I'm just going to move myself over here for a second, just so you can enjoy that. Showing just kind of like a little bit of a fun at the idea that we used to have a giant iceberg, and now we've got something that a polar bear can barely stand on. And back I go. So, first off, it's very important for us to differentiate between climate and weather. Weather refers to atmospheric conditions that occur locally over short periods of time. So if it rains out, or if you have a drought, or if you have a snowstorm, they're usually from minutes to hours or days even. Sometimes even weeks can be considered weather. Familiar examples to include even more, you got your rain, you got snow, clouds, winds, floods, thunderstorms, those types of things. Things that are generally more or less short-lived over the course of, what climate is considered, on the other hand, which is a long-term regional or even global average of temperature, humidity, and rainfall patterns over seasons, years, even decades. So we're looking very big picture when we're talking about climate versus weather. And that's important because you will often hear people discussing how climate change can't be real, for instance, or that global warming can't be real because it was a very cold winter. That's looking at weather. That's not looking at what climate is over the course of, patterns over averages of temperatures over years and decades. So, global warming refers to the long-term warming of the planet since the early 20th century, and most notably since the late 1970s due to the increase in fossil fuel emissions since the Industrial Revolution. It goes without say that when the Industrial Revolution happened and we started burning fossil fuels much more, the increased carbon dioxide and just greenhouse gases in general is what's really started affecting how much we're impacting our planet. Worldwide, since 1880, the average surface temperature has gone up by about 1 degree Celsius, or 2 degrees Fahrenheit if you're an American, relative to the mid-20th century baseline, which was found between 1951 and 1980. They use that kind of those years for like a baseline. This is on top of about an additional 0.15 degrees Celsius of warming from between 1750 and 1880, around the time of the Industrial Revolution. So, driven by capitalism, the Industrial Revolution was the beginning of an era of burning coal and fossil fuels with no regard to the environment. There are actually news articles that show, in some cases, that they were aware that there might be an effect on the environment and they just didn't care. So, climate change, on the other hand, refers to a broad range of global issues created predominantly by burning fossil fuels, which add heat-trapping gases to Earth's atmosphere. These phenomena include the increased temperature trends described by global warming, but also encompass changes such as sea level rise, ice mass loss in Greenland, Antarctica, the Arctic, and mountain glaciers worldwide, shifts in flower plant blooming, and then even just extreme weather events. So, the Earth's climate has changed throughout history. This is not news to anybody that's even heard of or watched, the movie Ice Age. Just in the last 650,000 years, there have been 7 cycles of glacial advance and retreat, with the abrupt end of the last ice age about 7,000 years ago, which marked the beginning of the modern climate era and of human civilization in general. Most of these climate changes are attributed to very small variations in Earth's orbit that change the amount of solar energy that our planet actually receives. So, the current warming trend is of particular significance because most of it is extremely likely, and when I say extremely likely, I'm talking greater than 95% probability, to be the result of human activity since the mid-20th century and proceeding at a rate that is unprecedented over decades. Earth-orbiting satellites and other technological advances have enabled scientists to see the big picture, collecting many different types of information about our planet and its climate on a global scale. This body of data, collected over many years, reveals the signals of a changing climate. So, I actually have this link here that if you guys want to take a look at it, I'm going to try and pop onto it quickly. But this kind of shows how about they how our Earth's climate has just changed. Our temperature has changed over the course of, its history, essentially. So scientists use different sources just as a starting point here to determine past climate. They use buried sediments at the bottom of the oceans. They take tree rings from trees, because trees can live hundreds and thousands of years in some cases. They take coral reefs, and then they take glaciers and ice caps as a couple of examples to determine the temperature. You can determine precipitation. You can even determine calamities. Example of a calamity, just as an example, you can actually look at the tree rings on a tree, and if there's like a burnt ring like in the middle or closer in the inside of it, you can assume that that year for that tree was some sort of fire or something along those lines. And then the further out you keep looking, you can see like how widespread that fire was. You can use that exact same kind of ideology to determine like again, precipitation patterns and temperatures. So I'm going to go, I'm going to be scrolling for a really long time with this. You can kind of see here on the scroll bar on the side that it's got quite a bit to it. So I'm not going to go over every single point here, but I'll go over some of the more interesting ones. So what's important again is they're using the average, so 1961 to 1990 average, if you can see at the top there, for what our normal would be, our zero baseline. So anything below that is colder in terms of the average, and anything on the other side on the right is warmer than that. So as you can see, it started off colder. Start of our timeline, 22,000 years ago, Earth is 4 degrees colder than during the late 20th century, which is again 1961 to 1990. And it shows here that Boston is buried under almost a mile of ice, and the glaciers reach as far as south as New York City. So quite a bit of ice, quite cold is kind of the general idea of this part of it. And then the world starts to warm up, and you can see this line continuing to go. Changes in the Earth's orbit mean that more sunlight reaches the polar ice and the ice sheets start to melt. Temperatures have been creeping upwards, but around this point CO2 levels start to climb, and then the warming speeds up. So there is one little caveat that they notice here. Basically what it's saying is that there is not a high chance of very like large fluctuations. So when they get this like dotted line they've created, which is based off of data derived from scientists, your data probably looks like something like this in reality, or maybe a little bit of fluctuation like that, or maybe there's even a single spike for a single point or a single year or what have you, but you're not going to see like a mountain essentially where you're going to see like a huge change for a long period of time, because that would actually adjust that entire line. So temperature continues warming up. Warming up. Well, at this point, this is how early in our lifetime this is. Humans have just domesticated dogs. The woolly rhino has gone extinct. The ice sheets withdraw from Chicago. Humans settle Abu Huraira in Syria. And then they start declining again. So this is, again, there's the different ice ages, the different fluctuations in our temperature that I noted at the beginning of our presentation. And it explains here that it's probably due to ocean circulation, due to the floods of cold, fresh meltwater flowing into the Atlantic. It just cools everything again, and then everything starts warming again. And at this point, temperatures reach modern levels, but this is still only 9,000 BC, right? So then it continues going. Cattle's domesticated, so again, pretty early. Ice sheets retreat across the Canadian border. There's our shout out. And then the temperatures start to level out slightly above the 1961 and 1990 levels. And then they stay around this for a while. We develop copper metalworking. At this point, we're at 5,000 BC. Invention of the wheel. Horses are domesticated, mummification. And you're seeing like where we start getting more idea of like the historical stuff that we've been doing, right? So there's a lot more points being brought in here, like Great Pyramids are constructed, Stonehenge is completed, chariots developed, alphabetic writing developed. But as you can see, we're kind of trending along this line, right? And you can see like over the course of this whole thing, it's been pretty gradual, a lot of this stuff, right? And then you get closer to real day. So 500 CE, so that's only like 1,500 years ago. 1,000, slightly cold. And then we hit S here. And you can see airplanes, world wars, nuclear weapons, internet, blah, blah, blah. But look how quick that goes. And so it's showing best case scenario, assuming immediate massive action to limit emissions, which is basically probably saying like zero carbon emissions, which if we're being real is probably not going to happen, and or not something that's very likely to happen. That would still drop it considerably. An optimistic scenario, and then our current path just continuing to fly up here. And I don't think the temperature was ever in that range if I just keep my mouse along that. So why is that bad? Well, that's what we're going to start discussing a little bit here. So the heat trapping nature of carbon dioxide, and oh, by the way, as I said, this presentation is available. So if you want to actually take a look at that link and kind of scroll through it yourself and see some of the other little notes that the artist wrote in it, by all means, feel free to. It's a fun little read. But back to this. So the heat trapping nature of carbon dioxide and other gases was demonstrated in the mid-19th century. So as I said, they were aware of it. They just didn't care because it would cut into profits potentially or something. Or maybe they just didn't realize how big of an issue it could be. I don't know. I wasn't them, right? Their ability to affect the transfer of infrared energy through the atmosphere is the scientific basis of many instruments flown by NASA. There is no question that increased levels of greenhouse gases must cause the Earth to warm in response. Ice cores drawn from Greenland, Antarctica, and tropical mountain glaciers show that the Earth's climate responds to changes in greenhouse gas levels. Ancient evidence can also be found in tree rings, ocean sediments, coral reefs, and layers of sedimentary rocks. I kind of mentioned that part already. And then the current warming is occurring roughly 10 times faster than the average rate of ice age recovery warming. That comic kind of showed that, just how hard it spikes up there at the end. The planet's average surface temperature has risen about 1.62 degrees Fahrenheit, or just shy of 1 degree Celsius, since the late 19th century, a change driven largely by increased carbon dioxide and other human-made emissions into the atmosphere. 1 degree probably does not sound like a lot, but it is. What you got to consider is that that's the global average temperature being risen by 1 degree. And I don't mean this in a way that like it's only the average, so in some spots it's higher and then some spots it's lower. Although that is the case, that's not the important part. The fact that everything is going up is not good, because everything has thresholds that they change state at. Ice being a big one. Even a couple degrees difference, or even 1 degree difference, you can start seeing ice beginning to melt, and more water, and just entire changes to ecosystems as a result. Think about how finicky some of the plants you might have in your own house can be. Imagine subtle changes to their environments might have on just forests and jungles and animals, livestock, even crops that we produce. Most of the warming occurred in the past 35 years, with the 5 warmest years on record taking place since 2010. Not only was 2016, this is an important part, which is why it's underlined, the warmest year on record, but 8 of the 12 months that make up that year, from January through September, with the exception of June, were the warmest on record for those respective months. There's actually a really interesting graph on Reddit, if you guys go on there. And it shows like how the temperature is like increasing, and it's like a circle. I'm doing a really bad job of explaining how it looks. If you know what I'm talking about, then you know exactly what I'm trying to describe here. But it shows a really cool way of showing how our temperature has increased through the years. So the oceans have absorbed much of this increased heat that's come from having increased carbon dioxide emissions, with the top 700 meters of the ocean showing warming of more than 0.4 degrees Fahrenheit since 1969. The ocean is the largest solar energy collector on Earth. Not only does water cover more than 70% of our planet's surface, it can also absorb large amounts of heat without a large increase in temperature. We'll discuss this more in one of the last lectures about the aquatic environment, but basically, as I just stated, water is an excellent medium for absorbing heat. This tremendous ability to store and release heat over long periods of time gives the oceans a central role in stabilizing Earth's climate system. Not only is it important that they can hold that heat, but they're excellent for moving it around. The currents and the undercurrents that are throughout the oceans are vastly important to the climate that we enjoy. So Increasing concentrations of greenhouse gases are preventing heat radiated from Earth's surface from escaping into space as freely as it used to. Most of the excess heat is being stored in the upper ocean. As a result, upper ocean heat content has increased significantly over the past 2 decades, which is basically what it's showing here. The main source of ocean heat is sunlight. Additionally, clouds, water vapor, and greenhouse gases emit heat that they have absorbed, and some of that heat energy also enters the ocean. So waves, tides, and currents constantly mix the ocean, moving heat from warmer to cooler latitudes into deeper levels, which is what I was explaining with the different currents and undercurrents that are super important for our climate. Heat absorbed by the ocean is moved from one place to another, but it doesn't disappear. Because remember, heat is a form of energy after all, and remembering the first law of thermodynamics, energy cannot be lost. So the heat energy eventually re-enters the rest of the Earth's system by melting ice shelves, evaporating water, or directly reheating the atmosphere itself. Thus, heat energy in the ocean can warm the planet for decades after it was absorbed. If the ocean absorbs more heat than it releases, its heat content increases. Knowing how much heat energy the ocean absorbs and releases is essential for understanding and modeling global climate. Historically, taking the ocean's temperature required ships to dangle sensors or sample collectors into the water. And this is the way that we try and determine the climate, like how the water absorbing heat is inducing change on our climate. This time-consuming method that they used to use could only provide temperatures for a small part of the planet's vast ocean, right? You'd only really get it for that specific area and that specific time. To get global coverage, scientists turn to satellites that measure the height of the ocean's surface. As water warms, it expands, so estimates for ocean temperature can be deduced from sea surface heights. To get a more complete picture of ocean heat content at different depths, however, scientists and engineers also use a range of temperature sensing instruments. Among these are a fleet of more than 3,000 robotic floats that measure ocean temperatures around the world. They work similarly to how a submarine might work. They're known as Argo floats, and the sensors drift through the ocean at different depths. So every 10 days or so, according to their programmed instructions, they rise through the water, recording temperature and salinity as they ascend. When a float reaches the surface, it sends its location and other information to scientists via satellite and then descends again. So if you look at this as a timeline, it's floating on the top there, transmitting its data. Then it slowly descends to its destination, which in this case is 1,000 meters or a kilometer down. And it drifts at that static level for 9 days approximately. Then it descends to even bigger, to a greater depth, so in this case to 2 kilometers down, 2,000 meters, and then it slowly starts recording its ascent back up to the surface. And then when it gets back to the surface, transmits its data, and then it goes again. Meanwhile, it's just been floating around, doing its thing. Hopefully it doesn't get eaten by, a whale or something. Scientists constantly compare data from satellites, from floats, probes, to verify that the values they produce make sense. It's a process of elimination. If you have in this case, if we look at this, we have 3,000 floats. If you have 2,999 floats that say the temperature is 30 degrees, and then you have one float that says 1,000 degrees, that's an extreme example, but that's kind of like the gist of what they're doing. They process the range of measurements to calculate an estimate for global average ocean heat content every 3 months. Converting the temperatures to joules, which is a standard unit of energy, allows them to compare heat in the ocean to heat in other parts of Earth's climate system. So another interesting pattern is the contrast between much higher than average heat content in the North Atlantic and much lower than average heat content in the waters south of Greenland. According to the report, this heat buildup in the North Atlantic has persisted since 2009, and the lower than average heat content south of Greenland has been in place since at least 2014. So scientists aren't entirely sure why this is the case, maybe associated with a reduction in what's called the Atlantic Meridional Overturning Circulation, which is essentially a current. And what this current does is it has northward flows of warm, salty water in the upper layers of the Atlantic, and then a southward flow of colder, deeper waters. This current has slowed over the last couple, 150 years-ish, which could impact agricultural output. It could change ecosystems, and it could trigger other climate trigger tipping points. It's considered a very important component for Earth's climate system due to the water and temperatures it shifts around. More than 90% of the warming that has happened on Earth over the past 50 years has occurred in the ocean, which kind of also makes sense considering we were just discussing how excellent the ocean is at absorbing and maintaining and retaining that heat. Recent studies estimate that warming of the upper oceans accounts for about 63% of the total increase in the amount of stored heat in the climate system from 1971 to 2010. And warming from 700 meters down to the ocean floor adds about another 30%. Averaged over Earth's surface, the 1993 to 2017 heat gain rates are 0.36 to 0.4 watts per square meter for 0 to 700 meters of the ocean's depth, and 0.19 to 0.35 for depths of 700 to 2,000 meters. So less than a watt per square meter, right? Doesn't sound too bad, it just sounds like a small change. But if you multiply by the surface area of the ocean, which, there you go, more than 360 million square kilometers, that translates into an absolutely colossal global energy imbalance. It means that while the atmosphere has been spared from the full extent of global warming for now, heat already stored in the ocean will eventually be released, and it will commit Earth to additional warming in the future. This is part of the problem, as we will continue discussing. They talk about it in the movie that is assigned for this week, Before the Flood. Even if the entire world collectively decided to use only green technology immediately, there would still be the lingering effects of what we've done so far. The impacts that we are currently seeing on the environment are not from emissions that we are releasing today. They are emissions, the impacts that we are experiencing currently, they're from emissions that we released roughly 10 years ago. It looks like the sun is starting to come through the blinds on my face. It's going to give an interesting little effect there. Sorry if that bothers anybody. So, warming of ocean water is raising global sea level because water expands when it warms. Combined, just like most materials, honestly, right? The more you heat something, the more excitable it gets, the more it expands. And you can see that even when it changes forms, right? When water heats to the point that it turns into steam, steam expands, right? It takes up more space than it does as water. Combined with water, weighs more, I guess. But combined with water from melting glaciers on land, the rising sea threatens natural ecosystems and human structures near coastlines around the world. And a staggering amount of our population lives by the water because, guess what? We as humans, we love our water. We love the ocean. We love the beaches. We love the lakes. So we're right by there. We will be definitely affected by this with sea levels rise. There's what's the term you Google? If you go on Google and you put in global sea level model, something along those lines, you can actually find an interactable map that will. I'm going to turn off my mic. Turn off my mic. That'll make a great presentation. I'm going to turn off my webcam just because that's actually irritating me a little bit. Sorry about that. You Google something like global water level model or something like that, like climate change water model or something along those lines. And there's an interactable map that you can play around with where you can put in basically how much the water level would rise by. So like 1 foot, 2 foot, 3 feet, all the way up to 10, I think. And it will show you how much of the coastline actually gets inundated by water. There's even little icons on the maps where you can actually click on monuments or historical just things that are well known, and it will show you how much the water would actually come up on them. It's very interesting. So warming ocean waters are also implicated in the thinning of ice shelves and sea ice, both of which have further consequences for Earth's climate system. Again, because water expands, right? When it turns from ice into water, it will expand further and then just take up more space itself. Because ice floats. You've seen that with the iceberg that sunk the Titanic, with the ice you throw into your drink. ice floats. So a giant chunk of it is actually, you know, it's like, I know displaces the water as it's floating there, but that doesn't take account the water or the ice that's, on land that melts and enters our oceans. Finally, warming ocean waters threaten marine ecosystems and human livelihoods. For example, warm waters jeopardize the health of corals and in turn the communities of marine life that depend upon them for shelter and food. This is again coming back to our keystone species that we discussed back in one of the earlier weeks. Ultimately, people who depend upon marine fisheries for food and jobs may face negative impacts from the warming ocean. The Greenland and Antarctic ice sheets have decreased in mass. Data from NASA's Gravity Recovery and Climate Experiment show Greenland lost an average of 286 billion tons of ice per year between 1993 and 2016. Think about how much that is. 286 billion tons per year, while Antarctica lost about 127 billion tons of ice per year during the same time period. The rate of Antarctica ice mass lost has tripled in the last decade. Glaciers are retreating almost everywhere around the world, including in the Alps, Himalayas, the Andes, the Rockies, Alaska, and Africa. And this picture just speaks for itself right there. Satellite observations reveal that the amount of spring snow cover in the northern hemisphere has decreased over the past 5 decades and that the snow is melting earlier. For those of us who shovel our driveways, that probably sounds like a positive to us. Global sea level rose about 8 inches in the last century. Again, 8 inches probably doesn't sound like a lot, but the rate in the last 2 decades is nearly double that of the last century, and it's accelerating slightly every year. So, although this picture that I'm showing here is probably not entirely likely, you got to consider that even a couple feet of increased ocean water, like the height of the ocean, is pretty drastic, especially if you consider how close, as I said, many of our cities are to the beaches and just the oceans. Both the extent and thickness of Arctic sea ice has declined rapidly over the last several decades. So this is showing that in 1988 or 1980, the ice went all the way out to here. To 1998, it was only up to here, and to 2012, it was only to here, and it's only gotten worse since. The number of record high temperature events in the United States has been increasing, while the number of record low temperature events has been decreasing since 1950. The U.S. has also witnessed increasing numbers of intense rainfall events. This is another thing that is not talked about nearly enough in climate change, is just how much we're experiencing more catastrophic events, not necessarily rainfall events, but you could start seeing more tornadoes. Hurricanes is a big one. Snowstorms, those types of things. Again, I will talk about this more in the next 2 lectures on the terrestrial environment and then on the aquatic environment, because there's a lot to cover with that. I want to, in regards to climate change, I wanted to split it up to be fair. Since the beginning of the Industrial Revolution, the acidity of surface ocean waters has increased by about 30%. This increase is the result of humans emitting more carbon dioxide into the atmosphere and hence more being absorbed into the oceans. The amount of carbon dioxide absorbed by the upper layer of the oceans is increasing by about 2 billion tons per year. And it goes without saying that acidifying our oceans is probably not great for the life that lives in it. It also takes away its ability to calcify things, which is also pretty bad. The industrial activities that our modern civilization depends upon have raised atmospheric carbon dioxide levels from 280 parts per million to 400 parts per million in the last 150 years. The panel also concluded there's a better than 95% probability that human-produced greenhouse gases such as carbon dioxide, methane, and nitrous oxide have caused much of the observed increase in Earth's temperatures over the past 50 years. In other words, it's our fault. Since 1750, the average amount of energy coming from the sun either remained constant or increased slightly. If the warming were caused by a more active sun, then scientists would expect to see warmer temperatures in all layers of the atmosphere because all layers of the atmosphere are influenced by the radiation coming from the sun. Instead, they have observed a cooling in the upper atmosphere and a warming at the surface and in the lower parts of the atmosphere. This is important because that means that greenhouse gases are being trapped in the lower atmosphere, which is exactly what greenhouse gases do. There are quite a few overall concerns for human health as well, as you can imagine. This picture shows just basically a bunch of city smog, which is pretty evident that poor air quality is a possible problem that happens with climate change. Some people are more vulnerable to illness or death. You might know some people that are more vulnerable to illness or have susceptibility to things. Young children, the elderly, those who are already ill, they're less able to withstand high temperatures, poor air quality, lack of food and water, those types of things. Temperature extremes and smog hit people with heart and respiratory diseases, including asthma, particularly hard. So smog is, as you can imagine, really bad for somebody with asthma. The greater the level of atmospheric greenhouse gases, the greater the amount of gases trapped at the surface in the troposphere. That goes without saying. Climate change affects humans in many, many ways. This chart kind of goes over a good number of them, but it keeps it pretty simple. The heat of the sun to the air we breathe, humans rely on the atmosphere that we live in to keep us alive. So as you can see, there's quite a few different things that all stem from these four things that are involved with climate change. You have your rising temperatures, which causes more extreme weather, which there's also the rising sea levels, and then of course there's the increasing carbon dioxide levels. And all of these cause their own things: extreme heat, severe weather, air pollution, changes in vector ecology, increasing allergens, water quality impacts, water and food supply impacts, environmental degradation. Extreme heat can cause, deaths and cardiovascular failure, people getting heart attacks. Severe weather can cause injuries and fatalities, flooding, right? Tornadoes, hurricanes. Air pollution cause asthma, cardiovascular disease, or just impact these people more, and then you can get even further death. Environmental degradation can cause forced migration, civil conflict, mental health impacts. It can destroy even just cities themselves if you have severe environmental degradation in the form of erosion or just mass flooding from, rising sea levels. Water quality, if you have rising sea levels, you can have things getting flooded, which impacts your water quality with cholera, cryptosporidiosis, Campylobacter, leptospirosis, harmful algal blooms, respiratory allergies, asthma. I can go on and on reading through this, but this is only a snapshot of some of the things that climate change can impact with human health. It's a big, big deal. And that kind of brings us to our conclusion for this week, at least. As I said, this is kind of going to be an introduction to climate change as a topic. The final 2 weeks are really going to hone in on specific areas of it. So the Earth is a complicated mix of chemical reactions and self-balancing temperature regulators. Human impact changed these formulas into a future of global warming. For our sake, for our children's sake, for nephews' sake, for just the next generation's sake in general, let's hope we're able to control these temperature increases for the future generations to come. We need to make sure that we can produce a world that's sustainable so that when we leave it, hopefully many, many, many years from now, that whoever's left behind is not left to deal with our mess, right? It's the polite thing to do. So that brings us to this timeline again. So there's the terrestrial environment presentation I will be going over next week, which is going to be dealing with how climate change impacts the terrestrial environment, so land. Assignment number 3, green technology assignment, is due tonight. And from then on, we have our Before the Flood video assignment due, which will be due Friday, April 1st at midnight. That video will be released with this presentation, so please watch that. It stars Leonardo DiCaprio, who, if you're not familiar with him, honestly, that would be surprising first off, but he's a big environmental activist, so it's not surprising that he's involved with it. And then we also have on April 1st, Friday at midnight, essay assignment number 2 on wildlife and climate change. That will also be due. That's your final essay. And then on Friday, April 15th at midnight, you have the One Ocean video assignment due. And then finally on April 18th, Monday, I will have the final exam test. It will be available for you to do. It'll be available all day on that. There is a presentation the week before our final test where we're going to go and review through a lot of our material. And I'll give you more details on the final test as we approach it, get closer to that date. But that week in particular, I'll probably spill the beans on everything as far as what that final test will contain. And with that, that's the end of this presentation. Hope you enjoyed it, and I'll talk to you guys next week. If you have any questions, as always, feel free to reach out to me via email. You can use the discussion board on Blackboard. You can request a meeting, anything you want. Let's get her done. Have a good week, guys.